Oh, great.
Okay, our next speaker is Jay Wright from Boise State University, and they'll be talking about molecular beam epitaxy synthesis and characterization of hexagonal scandium ferrite films. Let's welcome our speaker.
Good afternoon. My name is Jay Wright, as mentioned, and I'll be doing my talk on molecular beam epitaxy synthesis and characterization of hexagonal scandium ferrite films, and these are epitaxy stabilized. This is in conjunction with our collaborators at Cornell with Schlom's group, and it's supported by Paradigm Proposal and by the National Science Foundation. So molecular beam epitaxy, most of you are familiar with. It's basically heating up elements from the periodic table, and they will sublime through ultra-high vacuum and land on a substrate material. In our case, it's a sapphire aluminum oxide material, and this grows our crystalline structures in monolayers. So we basically are stacking layers on top of each other to create these cool structures. And in our case, it's scandium and iron atoms that we're stacking. And this is the reactor that we use, where we have O3. We have our fusion cells, our samples mounted here, and then we have reflection high energy electron diffraction for monitoring in situ growth conditions. And I'll be referencing a paper by Lauren Garten where she was interested in this P63CM phase where we have this layered growth condition. The ground state phase is less interesting to us because it doesn't have some of these ferroelectric behaviors that we're interested in getting out of our epitaxy stabilized scandium ferrite. So this is what the structure looks like. The red atoms represent the oxygen, where we use O3. These gray ones represent the scandium atoms. And in the center of these polyhedra are iron atoms. And this is a different material shown, but it is the same phase of material, so you can get an idea of what we're looking at. We're interested in this material because it exhibits evidence of multiferroic behavior where there's some coupling between our ferroelectric behavior and our ferromagnetic behavior. And it requires this layered shuttering technique in order to produce this. So in bulk, it's a Bigsbyite stable polymorph where we don't have any ferroelectric behavior because it's a central symmetric unit cell. And as it's thin film, with this epitaxy stabilized growth technique, we get a hexagonal polar unit cell. And the reason we're interested in it is some of the applications that could be realized if successful. So one of those is magnetoresistive random access memory, or MRAM, where we could basically store information in magnetic domains rather than a current flow or an electric charge. Magnetic field sensors, and tunable microwave filters. And again, this is just an illustration of what our material looks like in the P63CM phase. And this is what we get to see while we're growing the material. So this is images from reflection, high energy electron diffraction, where we have the 1 bar O and the 1 O. And from left to right, this is what we see while it's hot. And as it cools, we see this phase develop. And what's interesting is around 500 degrees, we begin to see faint lines showing in between these first order diffraction patterns. And what it indicates is that it's taking this hexagonal P63CM phase, and it's really difficult to distinguish when these faint lines appear because they are extremely faint. So this is a complete approximation, but as it cools, those begin to form, and what it represents is in reciprocal space, the unit cell is 1/3 the size, and in real space, it's about 3 times the size. And this is the phase that it's in while it's hot, which is P63 over MMC. So what I'll be doing throughout this presentation is comparing 2 different shuttering techniques. So this is flux-matched MBE, where we're basically matching the flux of scandium and iron. Both of our samples are roughly 80 nanometers, and the major difference, we tried to keep both of these as similar as possible with the major difference of a shuttering time, where we have one shuttering time of 33.74 seconds, and another shuttering time of 35.29 seconds. And these are not arbitrary values. They were selected by STEM and XRD data from a paper I referenced earlier, Lauren Garten, and then that's the in-plane lattice parameter of 5.85 angstroms. Our 35.29 seconds is calculated using an in-plane lattice parameter of 5.72 angstroms, and that's using reciprocal space mapping from experimental data. And one of the first characterization techniques we look at when we're growing these is X-ray diffraction, because we want to determine the stoichiometry of the film. Unfortunately, as you can tell, they're both really, really similar. So we're interested in the 004 peak, which is this one right here, and they look identical with the exception that there's a slightly different peak intensity, where we have a higher peak intensity for our shorter shutter time. And we also have a bit of phase impurity beginning to form on the 004 peak, and you see a little bit of asymmetry in it. X-ray diffraction is a really difficult way to compare the crystallinity and purity of some of our samples. Another way we can do it that's visually easier to look at is by probing the surface morphology using atomic force microscopy. This is our lower shuttering time, and this is pretty common for some of our higher quality growths to see images such as these. With our higher shuttering time, however, we have some of these faceted shapes begin to form, which we believe indicates possible iron precipitates, which could be indicating the Bigsby I phase impurity beginning to form. So these were not fantastic growths and did not give us what we were looking for due to the precipitates on the surface. Furthermore, we did Raman spectroscopy of both samples. The green arrow represents our peak of interest. This is our substrate material. And with higher temperatures, we do see a Raman shift in both samples. They had really similar behavior. However, when looking at our transition temperatures, we did have a slight shift, where for our shorter shuttering time, we had approximately 825 degrees Kelvin, where our ferroelectric behavior was diminished, and approximately 850 degrees Kelvin, where our ferroelectric behavior was diminished with our larger shuttering time. Unfortunately, we have a high degree of error in our accuracy with measuring these transition temperatures. So that's plus or minus approximately 50 degrees. So there may have been a shift, but it's very hard to tell because it's a broad range for our error. What we can say is that there is ferroelectric behavior in our lower temperature range, and that ferroelectric behavior diminishes toward our higher temperature range around 800 degrees Kelvin for both samples, with a slight shift possibly in our shorter shuttering time. So I hope I've convinced you that our shorter shuttering time actually produced higher quality samples as seen in X-ray diffraction, atomic force microscopy, and Raman spectroscopy. And if we agree that the shorter shuttering time produced higher quality films, I'd like to show you some of the other stuff that we've been doing with these higher quality films, which includes some of the ferromagnetic behavior using MPMS measurements. Our collaborator at Cornell University in Daryl Shalom's group performed MPMS measurements to determine the needle temperature, which was taken by extrapolating data kind of in the steeper portion here. And what they found was that it agreed with the Journal of Materials Chemistry for the highest recorded needle temperature for this material. And this is basically just the temperature where an antiferromagnetic material goes through this transition to a disordered paramagnetic state. But it's exciting for us because it agrees with the highest recorded temperature currently for this material. Additionally, we looked at the out-of-plane lattice parameter by using reciprocal space mapping, where this is our substrate and the red box, and this is our sample film here. And we determined the lattice parameter was 11.70 angstroms, which agrees nearly with the current data of 11.60 angstroms. There may be some strain, which is worth exploring a little bit further as we continue to grow some of these films. So in summary, we determined that the highest quality films were grown with flux-matched MBE using the shorter shutter time of 33.74 seconds. With the shuttering time, we observed a needle temperature that was in agreement with the highest needle temperature currently recorded in the Journal of Materials Chemistry. And some of the future studies that we want to do with hexagonal scandium ferrite include using paradigm laser heating to do some high temperature absorption controlled MBE, where we basically flood the chamber with the volatile constituent, in this case is iron. And we want to take Dr. Shalom's advice of turning up the heat and seeing if we can get maybe a higher needle temperature and higher quality films with this growth technique. So thank you for your attention, and I'll be happy to take any questions.
Questions for the speaker? Please use the microphone. I actually had a question.
Yeah, please.
It might be a bit stupid, but you mentioned this was the highest temperature recorded as you saw in the journal.
Yes.
So do you know the previous highest temperature recording? Did they use a similar shutter time, or was it a completely different way of preparing?
There is a paper, the paper I referenced for this is Journal of Materials Chemistry, which is talks a little more about what they did to grow the material. I believe it was a flux matched. It was also a flux matched MBE, but yeah, their anneal temperature was 195, and ours was in close agreement with it. So we're excited that we are producing that quality, and maybe with absorption control, we can push that a little bit. We just sort of were in the process of trying to push that window. So yeah, thanks.
Any other questions?
Oops. Oh, yeah, we believe it's not a stoichiometric film, and we think that shuttering time, having that where they're not they're matched, where they're calibrated to each other, so that's like by definition what flux matched MBE is. But we believe that if you have each shutter open too long and you're putting too many atoms during each growth, that eventually they will kind of stack on top and no longer be a neat row of like a single atom. So that's what we believe, and the surface is just where you see it show up, because that's where it kind of terminates. So that's what we believe is causing that kind of Bigsby phase impurity to start forming and be like iron oxide precipitates. So, yeah, thanks.
Okay, let's thank our speaker.